TRAX, Tracking in Complex Sensor Systems.
Hi, this is Kamiar. Today I am going to talk about new trends in radio network positioning. This work is also presented and published in the 18th Fusion Conference being held in Washington, D.C. 2015.
Hi, this is Kamiar. I'm an early stage researcher at Linköping University working on TRAX project.
At first, I would like to begin with the outline of this presentation. In the next few slides, some motivation behind this contribution is provided. Then, a general sensor fusion framework for positioning based on generic measurements is described, followed by available and improved measurements for positioning in wireless networks. After that, current and new trends in this area would be briefly presented, with some final wrap-up words in the last slide. Let's start with the motivation. Awareness of the position of a device, either in absolute terms or relative to a reference location, is becoming increasingly important. In either of these cases, what makes the main demand is accuracy. Examples of these areas are quite wide. Federal Communication Commission (FCC) continuously revises the 911 positioning requirements, initially with the requirements on network-based extending towards mobile-assisted ones. The technical report released in 2015 refined the requirements particularly for indoor positioning services. For example, the horizontal accuracy is said to be within a radius of 50 meters for 40% of wireless 911 calls, with the horizon of approaching to 80% of calls in 6 years. Location-based services could also be considered as another area with a high impact on our daily lives. Tracing the footprint of position-aware applications lead us to other areas such as gaming, navigation, logistics, autonomous vessels, proximity services, fleet management, and many others. One major consideration, however, is that the difference between what we could get from today's measurements and the existing demand on accuracy might not be negligible. Talking about the motivation, I would proceed to the next section, a general sensor fusion framework for positioning. The high-level perspective of the whole position estimation process, one could realize that parts of the positioning are performed on the chipsets or low layers, and then the low-level measurements are available to the higher layers where these information are fused. This section summarizes different levels of fusion in terms of signal models. In this regard, the three levels of fusion would be physical layer, spatial fusion, and modality and temporal filtering. The underlying notation of this framework is as follows. 3D mobile position at time t is given by p subscript t, and the known reference point is given by p superscript I. The generic measurement is then a function of both mobile and the reference positions plus some error term coming from measurement uncertainty. It must be noted that the function could be linear in parameters in some cases or nonlinear in some other types of measurements. Sampling at the receiver side could be modeled by this equation, where the impulse response of the channel is denoted by alpha and the time delay per incoming path by tau. Beta is also used for scaling. Position measurements are different resolution-wise, and that's because of different estimations of these parameters. Different types of measurements in the generic measurement model mentioned earlier could then be replaced by time of arrival corresponding to tau, time difference of arrival in case of unsynchronized receivers, round-trip time, angle of arrival, and the received signal strength proportional to the alpha. Measurement uncertainties denoted by errors then could be formalized this way for each type of measurement: TOA, TDOA, RTT, and RSS. In the level 2 or spatial fusion, given n transmitters, one could distinguish the measurement from each of them using this equation. There is a vast literature describing the principles of positioning. Examples could be trilateration for TOA, multilateration for TDOA, triangulation for angle of arrival, and trilateration or fingerprinting for RSS measurements. Using measurements of different modality or type is not a problem and is covered in the same nonlinear set of equation framework as mentioned already. New sensor information of other types could be entered at this stage. Barosensor with this model is one example of this kind. Additionally, in order to smoothen the estimated positions, one could also introduce filters at the third level. For that to happen, a decent motion model might seem vital. IMUs are good sources of having these motion models. By introducing three levels of fusion framework for the positioning, I would like to continue the talk by the available and improved position-related measurements in the wireless networks. At this point, I would like to give an example of one type of measurement and its corresponding error term. In order to model the received signal strength using channel modeling, one should notice that propagation also features diffraction effects which resembles as shadow fading, that is, a low-pass spatial process. A number of methods exist to deal with the diffraction error. The approach introduced here is based on the inherent feature of diffraction, meaning that by taking advantage of the high temporal correlation feature of diffraction, one could introduce the difference equation like this, resulting in the D term to be discarded. More information about other measurements also and their sources of uncertainty could be found in the paper. This table summarizes the accuracy of different types of measurements and their corresponding model. It's worth mentioning that timing measurements are based on synchronization techniques and also line of sight condition is investigated. Since the new LTE standard is also taken into account, one should notice that these values correspond to the best case scenarios. The next topic I would like to talk about is the new trends in this area. New trends can be divided into three main categories that I will go through them one by one. First, tighter information exchange. One trend that information and algorithms are shared between different layers in the classical OSI model of a communication system opens up for leaps in development. It means that there are sources of ambiguities that can be detected in the lower layers. For example, one could consider the power delay profile as in this figure. PDP can be seen as the estimated squared impulse response for tau equal to 0. From the figure, we can conclude that there are segments in the test when there is non-line of sight condition, there are many multipath components, and there is a strong spatial correlation in that nearby PDPs look quite similar. All these effects give rise to ambiguities in the estimated RSS and TOA. If the PDP was available in the higher levels, more sophisticated algorithms taking these facts into account could be easily derived. In addition to the information exchange train, we also have new and better information one. New timing measurements, massive MIMO, and ad hoc networks all lie in this category. I would like to go a little bit further into the timing measurement developments. The new proposal by Ericsson for indoor positioning enhancements consists of two main categories of RAT-dependent and RAT-independent algorithms, where RAT here means the radio access technology. All these proposals are very interesting, but going through them is beyond the scope of this talk. However, the new measurement part of RAT-dependent item is very well in line with this presentation. Going into this item, we face with different subcategories, among which Wi-Fi ranging via fine timing measurements is of our main interest. So in the next slide, I will go through this one. IEEE 802.11as already implements timing measurements or TM being an optional procedure, meaning that those stations who do not support this shall ignore its corresponding frame. After initiation of the process, the action frame makes it possible for the initiator to calculate its clock offset relative to the other stations. These are very well described in the technical report of the standard. This diagram explains different frames and initiation and calculation procedures of timing measurements. As you can see, in order to calculate the clock offset, the receiving station needs T1 and T4 being stamped at the sending station. As mentioned already, in the follow-up TM frame, the sending side transmits its captured timestamps. The next revision of timing measurements is the fine timing measurements FTM to be implemented in IEEE 802.11mc. However, there is not much information about it published already. According to a public report being published by Intel, it is going to be the same as its predecessor timing measurement with some improvements. Increased timestamp resolution from 10 nanoseconds to 100 picoseconds is one of them. The last part of the new trends is the new infrastructure that I am going to talk about in this slide. 5G and future radio network standards are all of these kind of new infrastructures. However, first of all, we should notice that 5G should not be seen as an evolution of 4G. The communication capacity will probably increase, but more importantly, it must be seen as an industrial application and an enabler of embedded systems such as IoT and machine-to-machine communications. Positioning, however, is one of the most important design specifications. The infrastructure illustrated in this figure contains different entities that each of them can affect the measurement resolution drastically. All the devices at the lowest layer are connected to their upper layer devices via short-range technology such as Bluetooth, Zigbee, etc. At the meantime, devices in the middle layer could vary from a simple user equipment acting as a gateway to a machine-type communication device. Different types of access of the middle devices could be an IP connectivity to another gateway, cellular access to the access point, or even an intra-connection to another device of the same layer via short-range technology. Finally, I would like to wrap up the whole presentation in few words. First of all, what can be seen from daily usages and application trends, position awareness is transforming from a nice-to-have to a must requirement. Depending on the area of usage, however, available measurements and as a result estimated accuracies vary. On the other hand, we have different trends of IoT, machine-to-machine communication, and autonomous vehicles. This talk aimed to provide an overall state of the art of this area and improvements in available measurements and also their sources of uncertainty. This would bring up ideas for new research directions. Well, at the end, I want to thank you for watching this video.
For more information about TRAX, please visit our site at trax.u20.nl.